Let's go ahead and take a look at example 1 from section 2.5. Suppose we're asked to solve the differential equation x squared plus y squared dx plus x squared minus xy dy equals to 0. If we went through all of the methods that we've kind of discussed so far, it's not going to be separable as it is. It's not a linear ODE. You could check for exactness. It's not going to be exact. But if we look at the coefficient function, so we know that m of x comma y is x squared plus y squared. This one's going to be homogeneous of degree 2. If I replace x and y with t of x and t of y, we get t x squared plus ty squared, which is equal to t squared x squared plus t squared y squared. Pull out your t, we get t squared times x squared plus y squared, and this was equal to the original function m of x comma y. So we know that m of, let me back it up. So we know that m of tx comma ty is t squared m of x comma y. Similarly, if we look at n of tx ty, n of x comma y itself was x squared minus xy. So this evaluation will give us tx squared minus tx ty, which is equal to t squared x squared minus t squared xy. Factor out the t squared, you get x squared minus xy, and then this is the same thing as the original n of x. So we also have that n of tx comma ty is t squared n of x comma y, which means that both m and n are homogeneous of degree 2, which means that our differential equation is homogeneous. Okay, so this shows us that our ODE is homogeneous. And the implication for that is that means we can solve this thing. We're going to solve it via using the substitution we showed in the last slide. So we should be able to solve this by letting y equal to u of x. And then we know that if we let y equal to u of x, then the implication is that from the differential, then dy is going to be equal to u dx plus x du. A similar derivation, and I didn't show this in the notes when I was explaining it last time, but there's an alternative substitution that would also work. Instead of letting, if you recall, where this u came from, is we ended up with showing the identity. We showed that m of 1 of, come back. We showed that, what did we show? We showed that x to the alpha m of 1 comma y over x was equal to the original function m of x comma y. And that kind of gave us the basis for the substitution. You can do this alternatively, where you could get a 1 in this position instead, and then it would lead to the alternative approach where you would have the substitution x equals vy, and then you would get something like dx equals v dy plus y dv, where you would solve for the function v. You would hope to find a solution v. Let me call it psi of x. And then the overall solution, would you come back here, it would be x equals psi of y, psi times y, where v is a function of x, by the way. So we have x equals psi of x, y. Then you would divide both sides by psi, and y would be equal to x divided by psi x would be your solution. Okay. You can do that. It's perfectly fine, but there's no reason to learn how to do it with a different method. If it's homogeneous, y equals ux always works, and it's perfectly fine for us. So that's what we're going to do. So let's go back and do our substitution. Again, everywhere we see a y, we're going to replace it with ux. Everywhere we see a dy, we're going to replace it with this differential. So our differential equation under the substitution becomes x squared plus, this is going to be ux squared dx plus x squared minus x times y, which is ux. Now I need to make some room. We need our dy coming in. dy is going to be u dx plus x du, and this whole thing should be equal to 0. Let's clean this up. We have x squared plus u squared x squared dx plus, this is going to give us an x squared minus u x squared u dx plus x du equals to 0. I can factor an x squared out of this part, so that's going to be helpful. We want to kind of start to separate our variables a little bit. So we're going to have x squared times 1 plus u squared dx plus, okay, I can kind of factor a x squared out of this. Factor out the x squared, we're going to have a 1 minus u bracket u dx plus x du equals to 0. Let's now distribute this term into the parenthesis. We have x squared times 1 plus u squared dx plus, we're going to get x squared 1 minus u times u dx plus x times x give us x cubed times 1 minus u du equals to 0. From here, we should be able to kind of separate this out. Let's go ahead and do that. Let's see, if it helps, we can probably, let's see, move maybe the du to the other side. So we have x squared (1 plus u squared dx plus x squared 1 minus u dx equals negative x cubed times 1 minus u du. We have a common dx term. We also have an x squared that's common, so we can factor that out. So I have x squared dx. Maybe I'll put it behind it. But I'm essentially factoring out my x squared dx that I have here. And when we factor that out, what that's going to leave us with is a 1 plus u squared plus, from this term, plus a 1 minus u. This is equal to negative x cubed 1 minus u du. Gonna need some more space here, run out of room. Okay. Simplifying what was in there, I don't want that to be gone. We have and I'll write it in standard order, we have u squared minus u plus 2 x squared dx is equal to negative x cubed 1 minus u du. And now let's separate our variables. I can divide both sides by the following. So I want to get an x, just x on this term, x on this side, which means I want to divide by that u squared minus u plus 2. I'm going to get rid of that. So I'm going to divide that to both sides. Consequently, we also kind of want to get rid of the x cubed that's here. So let me kind of go ahead and I'll divide by the negative x cubed, since really we're interested in solving for u. So it might be convenient to have a positive factor there for our u. And here's what we get. On the left-hand side, these cancel. We have x squared divided by negative x cubed. That's going to give us dx over x with a negative sign is going to be equal to, on the right-hand side, these things cancel. And we have a 1 minus u divided by u squared minus u plus 2 du. The left-hand side is an integration. The right-hand side, we're going to need to do some partial fractions. We have negative dx over x is equal to, this is 1 minus u. This denominator should factor as, oh no, it won't factor. So that will not factor, hold on one second.